Today we finish discussing some issues concerning geometrical optics, and we shall use the whiteboard, and then if you sit there, you see better. And then we shall use the slides that I sent you of the lecture #1 and go back to some other issue concerning the electromagnetic description of light, and in particular a microscopic model for the description of the refractive index in a medium that is helpful in our case. Now, you remember that we are giving some, let's say, short reminder concerning the results that you get from a course in general in geometrical optics. And during the last lecture, we discussed the simplest optical system that we can think of. That is a spherical surface that is separating two media with different refractive index. So you remember that if this is what we call the optical axis, then you can have a surface that is spherical with a certain radius of curvature. And this surface may separate two regions with a different refractive index. We said that if we consider a light source that is emitting spherical waves, and therefore in the view of geometrical optics is emitting optical rays, all optical rays that are emitted by the source are sent to one point that is named the image of that point. This is true only if you are in a so-called paraxial approximation. That is, if this angle is so small that you can neglect the difference between tangent alpha, sinus alpha, and alpha. This is the same approximation you make when you study the pendulum in physics. Okay, the simple pendulum. So in this paraxial approximation for the diopter, we have an equation that is governing the behavior of the diopter. That is the ratio between the refractive index of the input medium and the position of the light source measured with respect to the so-called vertex of the diopter, plus the refractive index of the second medium divided by the position of the image must be equal to the difference of the refractive indices divided by the radius of curvature. Remember that by convention in optics, the position of the source is positive if it is on the left-hand side of the vertex. The position of the image is positive if it is on the right-hand side of the vertex. The radius of curvature is positive if the center is on the right-hand side of B. Okay? These are the conventions. I forgot to say, but generally in optics, you assume that light is coming from the left. So we are, let's say, in the Western tradition rather than in the Arab tradition. Okay. Now, and this is what is called the diopter. We made some examples, and we have shown that there are two foci of this system, and that depending on the radius of curvature and the relative value of the two refractive indices, you can have that the foci are along one direction or they are in the opposite direction. By the way, I should restart the camera to be sure that you see me. But just a while, I'll do it. It's being reset. Just a while. And hopefully we have a camera. Yes, it is moving. Gun. While. Okay. So you should be able to also to see. Okay. Now, clearly, you in optics, you may have that an optical system is formed by several different surfaces that are separating many materials with different refractive index. If you will visit any website of a company producing optical microscopes, you will find a section concerning microscope objectives, and you will find the technical drawings of these microscope objectives. And then you will discover that if you look carefully to an optical, say to a microscope objective, then this microscope objective looks like this. And these drawings will show you that the system is formed by really many lenses. Like this, and so on, and so on. So there are many lenses inside an optical microscope. And generally, these lenses are constituted by media with a different refractive index. So it might be that here you have a refractive index N1, that in this lens you have N2, in between them you have A, and here you may have N3, and so on. So in general, you may have a system constituted by many diopters, many surfaces that are a portion of a sphere, which separate couples of materials with different refractive index. Now, of course, you might have that you have a surface like this, a surface like this, a surface like this. That is, you could have that these systems, these diopters, do not share the same optical axis, but they are somehow misaligned. then you call a centered optical system a system that is constituted by a number of diopters, any number of diopters, that are separating media with a different refractive index, N6, and they share the same optical axis. Share the same optical axis. Okay, this is a centered optical system. Now, surely it is possible to produce systems like this, but they have only very specific applications. Most of optical systems are like this, and they are, let's say, a succession of diopters. Now, it's clear that for an engineer, this is not a problem, because you can do the following. You can apply, given a source of light, you can apply the law of the diopter to the first diopter, that is separating the medium and 1 and 2. Then you calculate the position of the image of the first diopter. This image will become the source of the second diopter. And then you will apply the law to this, to this, to this, to this, and you can calculate the relations between the position of the source and the position of the image. Clearly, if every diopter is operating in the paraxial approximation, then you have a B-injective relation between S and I, as in the diopter, because you are in the paraxial approximation in any case. Okay? Now, this is not completely true in the application, because if you open the data sheet of a microscope objective, you will discover that many of these lenses are not spheric. They are aspheric. And this is done because you want to compensate the aberrations that come out when you operate at very large angles. Given that in a microscope objective, we shall see this, you operate at a very large angle, very often you are not in the paraxial approximation. So companies producing objectives are specialized in fabricating systems that are constituted by diopters that generally are not spherical and that are very carefully calculated. Keep in mind that if you buy a general purpose objective for general purpose applications used in the biology lab, this can cost 100 euros. But if you buy a total internal reflection objective for specific application in TIRF microscopy, the cost of objective is 25,000 euros. So there is a strong market for highly technological devices like this, even if an objective is somehow a system that is at least 100 years old. That's the why that the designs of these systems are really very carefully stored in the companies. Once I was in Vienna, in Germany, and there is a very nice museum of optics. You know, Vienna is the mother town of optics because Zeiss was born in Vienna and Habbe was born in Vienna, in Germany. And there are images of the end of the Second World War, 1945. The Americans had conquered East Germany. Most of East Germany was American. But then, in order to make a deal with the Russians, the Americans left the East Germany to the Russians, and the Russians left a part of Poland. There was a deal, and the Americans were in Vienna, and there are images of the museum, the Zeiss company, with thousands of boxes outside of the company, that were filled with documents that were then sent to West Germany, where a new Zeiss company was founded, Zeiss Oberhofen. Okay? So for 70 years later, there were two Zeiss companies, one in the East and one in the West. And the one in the West was a replica with the drawings of the objectives of the East. Okay? So keep in mind what would be today a secret like this, maybe the algorithm of Facebook or something like, or Google, something like that. Now, what is the simplest optical system that you can think of? The simplest optical system optical centered system, and we use it just as an example. The simplest system is what we call the so-called thick lens. What is a thick lens? Imagine you have the optical axis, and then you have a surface. Let me design it really very thick. Two surfaces, and say they have a radius or curvature R1 and a radius or curvature R2 that are separating two different media. Okay? We are doing it very simple already because we could think of having here N3 instead of N1. So to have three different media, but we make it simple and we assume that the entrance medium is the same as the exit medium, exactly as your colleague or me, we wear high glasses. There is a first surface of separation between air and glass, plastic, not glass, and a second surface of separation here from plastic to air again. But for example, in your eye, this is not the same. In your eye, you have air, the crystalline, and the water environment that you have inside your eye. So you should take this into account, but we make it very, very, very simple. Then how do you study this system? You do the following. You say, okay, if I have a source of light, this will be placed at a position that I call Q from the vertex. The beams coming from this source will go here to a first image. Let's call it I prime. And this image will be located in a position P prime, say like this. Now, since we are monkeys, we already told many, many times. And since all rays will go here, as a matter of fact, what is happening is that this image can be considered as a source of light because this is emitting rays. So the rays will continue like this, and they will be sent by the second diopter in a point that we name image. And of course, I can relate this Q prime and this P prime. Let's call it P, not P prime. You can relate the positions of Q prime and P prime. Okay. Now, if the thickness B of this lens is D, the thickness of this lens, then I know that this D is equal to P prime plus Q prime. Okay, because simply you see the design. Now you can say, okay, I can write the equation for the first diopter, and so I have N1 divided by Q plus N2 divided by B prime. It's equal to N2 minus N1 divided by R1. because this is the radius of curvature of the surface. You can write the equation for the second diopter. So you can write N2, that is the medium from which you are arriving when you go to that interface, divided by Q prime, plus N1, that is the arrival medium, divided by P, must be N1 minus N2 divided by R2. And you have these two coupled equations. You put them in a pocket calculator or in a smartphone, whatever, in a local calculation capacity device, and you can calculate out what is the position of the image. However, you can go to the limit of the so-called limit of the thin lens. So what is a thin lens? A thin lens is a lens which has got a thickness of the device that is much less than the radius of curvature and the coordinates of the image and the source points. So you consider thickness very, very thin. You can imagine that we would not like to wear eyeglasses that are 10 centimeters thick. We already don't like to wear eyeglasses because they make jokes of us, isn't it true? They make joke of us. Think if you would wear 10 centimeters eyeglasses, it would be the greatest shame. So all the efforts of people fabricating lenses was devoted in the past to get thin devices. Okay. Now, what does it happen if you go to the thin devices limit? You look here. You can. You understood the sketch, no? So, no, I can maybe remove this. We can take these two equations. First of all, we can say this is N1 divided by Q plus N2. Let me write properly. N2 divided by P prime equal to N2 minus N1 divided by R1. The second equations, I can write N2 divided, instead of Q prime here, I can work out Q prime from here. And instead of Q prime, I can write Q prime is D minus P prime. Okay? So I can write here D minus P prime plus N1 divided by P must be equal to N2 minus N1 divided by R2. Okay. Now what does it happen? This is still true for a thick lens. But what does it happen for a thin lens? It happens that this D is negligible. You can neglect it. Okay. And if you do this, you realize that this term here, is there a question from remote?
Yes, N1 minus N2 over R2.
Sorry?
The last equation.
Yeah.
You must write N1 minus N2 over R2.
Ah, sorry, I made a mistake because I was running. You're right. This is N1. You are right. This is N1. N1 minus N2. Yes, you are right. Should. Do you agree now? Can you hear me?
Yes, it's okay.
Okay. So you realize that these two terms are the same, but you have a negative sign here. So if you sum up these two equations, you see that when summing up, these two terms are can be summed up to 0. And then you get that n1 divided by q plus n1 divided by p is equal to n2 minus n1 times 1 over R1 minus 1 over R2. You get an equation like this, okay? So you get the so-called lens maker equation. This is lens maker equation. That is the equation that was used in the Middle Ages to fabricate lenses. You can write it in a different form. You can write, you can divide by n1, and so you have 1 over q plus 1 over p is equal to n2 minus n1 divided by n1 times the difference of the inverse of the radii of curvature of the two diopters. You get this, okay? And please keep in mind that you have 1 here because we assume that the two external media are the same. If the two external media would not be the same, then you could not factorize this term here, and the equation would be different. Okay? Now, since the lens makers, they were artisans, they are craft workers, they were not good in mathematics, very easily you understand that when you don't understand something, you simply give a name, okay? So you don't understand the vaccine, you call it no vax. You don't understand the green card, you call it no green card. You do not understand this formula, you call it the inverse of the focal length. And so the thin lens equation can be written here. Let me create a new page. 1 over q plus 1 over p must be equal to 1 over f, where this 1 over f is n2 minus n1 divided by n1 times the difference here, okay? And now it's really very clear why the lens makers are using as a unit in optics the dioptria. They are using the dioptries because this is the inverse of a length, and it's very simple to work out calculations in this way. Okay, now that tells us how do we represent a thin lens. We represent this in such a way where this is n2, this is n1, this is n1, and then we know that if the source is here, the rays will be sent to an image. If you are in the aparaxial approximation, this distance is q, this distance is p, okay? And sometimes students complain and they say, Professor, where should I measure this distance from? from here, or from the middle position. Always remember that you are approximating the lens with a thin lens, with a thickness that is 0, basically. So this is just a design that I made to let you understand how the things go on. Okay? Now, very often you work in the case in which you operate in air. So the external medium is air with refractive index 1. The lens is made out of a glass, and you generically call the refractive index n. And so the inverse of the focal length is n minus 1 times 1 over R1 minus 1 over R2. Okay? And now you should understand, okay, that this focal length can be positive, negative. We don't take into account the 0 value because it's trivial, but it can be positive or negative depending whether this refractive index difference is larger than 0, and depending whether this the difference between the inverse of the radius of curvature is larger or smaller than 0. Okay? And now look, if you fabricate lenses out of glass or plastic, typically the refractive index is 1.5, glass or a polymer, typically n is more or less 1.5. So n minus 1 is larger than 0. Okay? And therefore, if you have a lens like this, where you have two curved surfaces like this, what about this difference here? Is it larger or smaller than 0? Look, R1 is this one. Is it positive or negative? It's positive. R2 is this one. Is it positive or negative? Negative. Okay? So surely this difference here is larger than 0 because minus 1 over R2 is surely positive. Okay, so if you have a polymer or glass lens that has such two curved surfaces, so a so-called convex lens, because you have two convex surfaces, convex lens, then surely you know that the focal length is larger than 0. You have a positive lens. Okay? On the other hand, if you have a lens like this, with two curved surfaces like this, then how is it R1? It's negative. How is it R2? Positive. And the difference of the inverse of the radius of curvature, 1 over R1 minus 1 over R2, is surely less than 0. And so you know that surely this lens has a negative focal length. Okay? So you are sure that the convex lens has a positive focal, and the so-called concave lens has surely a negative focal length. Okay? But you could also have combinations of radius of curvature. You can have lenses like this, plano-convex. You can have lenses like this, plano-concave. You can have lenses in which the radius of curvature of the second diopter is larger than the radius of curvature of the first diopter. You can have lenses where you have a small radius of curvature here, and a small radius of curvature here. Depending on the radius of curvature, you can have positive or negative lens. But the two, say, really important cases are these two. For this reason, in optics, very often a lens with a positive focal length is represented with a symbol that is a double arrow like this. Okay, so in optics, you may find as a symbol of a lens a double arrow like this, because you are mimicking this shape here. And very often, a concave lens, so a negative focal length, is represented like this. A double arrow with inverted arrows at the ends, and this is representing a lens like this. Okay, you have many more degrees of freedom to design the optical system with respect to the diopter. Okay, now what does it happen if you have a lens with positive focal length? Okay, then you can define, and we represent it like this. Okay, then you can define a focus number one. What is the focus number one? Is the point where rays that are parallel and coming from infinity, so a plane wave, are focused by the system. Okay, and this will be the focal distance f1. How do you find out f1? You simply look at this equation. Okay, and you see that when Q is infinite, so when the source of light is an infinite distance, 1 over P is 1 over F. The coordinate of the image is exactly the focal length that you defined before. Okay? You can define a second specific point, that is the focus number 2. And what is the focus number 2? The point where you should put a point like source to get beams that are parallel. That is, beams that meet at an infinite distance. And this will be the coordinate f2. And you discover that if you put p equal to infinite, given that this equation here is symmetric with respect to Q and P, the position of the point where you should put the source is exactly at a distance f. So in a thin lens, f1 is equal to f2 is equal to f. In a thin lens, the two foci are at the same distance. Okay? That is the reason why if you take your eyeglasses, okay, and you do like this, you still see good. Try. You can use eyeglasses exactly the same, inverting them, and they work exactly the same. Okay? If you are astigmatic, this is not true, because if you are astigmatic, okay, you have an axis rotated like this, and when you rotate the eyeglasses, it will go down. But okay, okay, so you can use a lens, you know, like this or like that. It will do exactly the same work. Okay, there are some issues related to Fresnel coefficient, because if you have a lens like this and you send light like this, you have reflection at this interface and normal incidence, and the Fresnel coefficient has a certain value. But if you use the same lens like this, the reflection at this interface will be at a larger angle, and the reflection might be larger or smaller depending on the polarization. So in specialized optics, you always use lenses like this, not like that, even if you could. Okay, and now I don't go into the details, but it is clear that if I have a positive lens with two foci, and we call them F2 and F1, if I have a point-like source here, or not a point-like, you remember we use an arrow, okay? Then light coming from infinity, and let me draw it with a nice color. Light coming from infinity and passing by the point of the arrow will be sent to the focus, number one. Light coming from here and going to the focus, number two, will go here and will be sent here. So they meet here. So the image of this object, okay, is created here. So the image is real. What does it mean, real? It means that really the beams cross again where they pass through the lens. So the beams cross again here, and it is reversed. Okay, so a positive lens is operating like this. Okay, if you have a negative lens, say something like this, then what does it happen? That F2 is here and F1 is here because the coordinate of the foci is negative, so they are inverted. So if you have an object here, now it is difficult to draw this, no? What does it happen? The beam that is going here, what does it go? To F1. It must go to F1, so it's doing this. Okay? Then the beam that should go to F2 is transformed to a beam that goes here. Okay? So an observer that is here, that is watching light that is coming towards him, he thinks that light is coming from the intersection of the prolongation of these two beams. So the image here, the image is virtual, and right. What does it mean, right? It is up to the same orientation as the object. Okay, so if you are watching through a diverging lens, you see the object smaller and closer to you. Clear? Now, clearly, if instead of having a positive and negative lens, you can get a positive, and a negative lens by combining the refractive indices and the radius of curvature as you wish. Okay? And you can get many situations. So with this, we finished the overview in optics. We do not yet speak about the microscope objective and the microscope itself. We shall go back to the microscope later on when we shall introduce microscopy. Okay? So for the moment, we stop here. And always what we have to keep in mind is you have this law, and that this focal length is calculated by means of this formula. And always remember that in these formulas, there are conventions of the signs. The signs of these quantities, these are algebraic quantities, and they have a sign. Also F, also P and Q. They have a sign that is given by the convention in optics. Okay, are there questions about this? No. So we take 10 minutes rest, that we go to the slides, and then we start again.